Well, good evening, everybody. My talk today will be about one of the key pillars that underpinned the Allied forces' victory over Nazi Germany, leading to the liberation of Europe in 1945, and how a company based in Woolwich that had led a long-standing relationship with Germany played a pivotal role in that success. That company was Siemens Brothers, and the key pillar was Operation Pluto. In 1845, Carl Wilhelm Siemens came to England from Berlin to establish a branch of the engineering company founded by his elder brother, Ernst Werner Siemens, and his friend, Johann Georg Halske. It was slow progress, but by 1858, Carl Wilhelm had registered the Siemens and Halske Agency in London, providing engineering consultancy to the emerging telegraph market. At the same time, another brother, Karl Heinrich, set up a Siemens and Halske factory in St. Petersburg. He would later join Carl Wilhelm in London in 1869. Carl Wilhelm became a naturalized British subject under a warrant granted by Queen Victoria in 1858, and he changed his name to Charles William Siemens, although he always preferred to be addressed as William. In 1863, William Siemens founded his factory at Woolwich on land leased from the Bowater estate. The extended site is still there, bounded by the river, Eastmoor Street, Warspite Road, and the Woolwich Road. Incidentally, Warspite Road was originally called Trinity Street, but the name was changed in the 1930s. It was named after HMS Warspite, which was moored in the River Thames as a training ship for boys from 1876 until it was destroyed by arson in 1918. In 1865, a rift developed between William Siemens and Johann Halske over the submarine telegraph cable market, which Halske considered far too risky, so they went their separate ways. However, Halske retained a large equity stake in the London company, and it was re-registered as Siemens Brothers Limited later that year. The site adjacent to the river was chosen to cater for loading submarine telegraph cables. However, Siemens also made terrestrial cables and telegraph instruments, as well as telegraph poles and their furniture. A new headquarters building was erected on the site in 1865. Over the next 30 years, Siemens Brothers expanded into dynamo production and experimenting with electric lighting. This required additional buildings, and in 1881, a new 99-year lease was agreed with the Bowater estate. This covered the existing property, plus the land to the south between Harrington Street and Marsh Road, which is now Bowater Road, and east from the original factory to Trinity Street. This last image shows the factory in 1898. No HMS Warspite to the left of the chimney in the Thames, and the huge pile of wood at the east end of the factory. The story about the wood is a story for another day. At the beginning of the 20th century, Siemens Brothers continued to expand its product portfolio to include power cables, batteries, light bulbs, telephone instruments, telephone operator switchboards, and early automatic telephone exchange switching equipment. Once again, this necessitated further construction on the site. In the period between the two world wars, Siemens products continued to sell, but it was in the area of automatic telephone exchanges that a big new market was developed. Again, new buildings were required. In 1930, Siemens introduced the revolutionary Neophone, and more building was needed to accommodate its production. Despite Siemens Brothers' strong German links, which would result in confiscation of share capital, an internment and/or deportation of many German national employees during both World Wars, Siemens Brothers was responsible for several major technical developments that assisted the Allies in the First World War. This included field telephone systems and trench cable, but perhaps the most significant development was the ruggedized light bulbs for the Aldous and OL signal lamps, which were used by the Royal Navy and Army respectively in both World Wars and beyond. By the outbreak of World War II, the Siemens Brothers site had expanded to 35 acres, employing around 10,000 people, second only to the Royal Arsenal in the size of the site and the number of its employees. At that time, the demand for cable remained high due to bomb damage caused by German air raids, and once again, Siemens contributed to some significant military projects to assist the Allied forces. There was a high-speed motor uniselector used in what was then known as chain home, a key element in the revolutionary radio direction finding system. RDF would later become known by the acronym radar, which is of course radio detection and ranging. Siemens also produced the extremely robust light bulbs for the Churchill tank, without which it would have been inoperable due to the massive vibrations produced by the engine and drive systems. By November 1941, the United Kingdom stood virtually alone against the advance of the Third Reich. They had survived the humiliation of Dunkirk, which Winston Churchill described as a colossal military disaster. However, over 300,000 Belgian and British troops had been rescued from the beaches between the 26th of May and the 4th of June 1940. This led to Churchill's famous "We will fight them on the beaches" speech. Immediately afterwards, the conflict for control of the skies over Europe, known as the Battle of Britain, ensued. It lasted from the 7th of June 1940 until the 11th of May 1941, when the RAF secured victory and the Luftwaffe reverted to night bombing raids on British cities. At that time, public opinion in the USA was strongly against joining the war in Europe, and it wasn't until the Japanese attack on Pearl Harbor on Sunday, the 7th of December 1941, that this changed. The USA formally entered the war in Europe on the 11th of December 1941. Almost immediately, strategists switched their thoughts from defense and began thinking about the liberation of Europe. The story begins in early April 1942, when Lord Louis Mountbatten, the Queen's second cousin, and at that time Chief of Combined Operations, put a proposition to Geoffrey Lloyd, the Conservative MP for Birmingham Ladywood, Secretary for Petroleum and Head of the Petroleum Warfare Department of the Ministry of Fuel and Power. Mountbatten suggested that if a military campaign in Europe was to be successful, then there would need to be a pipeline across the English Channel to provide petrol, oil, and lubricants in bulk to support the armed forces. Lloyd put this to the experts in his department and their consultants, who had prior to the outbreak of war been working on pipelines across the Bristol Channel, the River Mersey, and the Thames. Their advice was that tidal and weather conditions in the English Channel, together with the risk of enemy action, would make it impossible to implement the proposal using any currently known land or sea construction method, which required pipes of 6 inches or more in diameter. However, the problem reached the ears of Arthur Clifford Hartley, Chief Engineer of the Anglo-Iranian Oil Company. Earlier, his company had solved the problem of transportation of oil over a very hilly route by the development of a flexible 3-inch pipe working at 1500 psi. Hartley recognized that such a pipe could deliver 100,000 gallons of fuel per day, the equivalent of 25,000 jerry cans, which was the method used for refueling vehicles in the field. So Hartley suggested to his chairman, Sir William Fraser, who was Honorary Petroleum Advisor to the War Office, that such a line could make a significant contribution to the problem, and that if multiple lines were built, it would have the major advantage of not having all their eggs in one basket. One obvious problem was that the pipeline would need to be laid quickly to overcome the tides and currents, and ideally, it should be laid in one operation without joints at sea, limiting the risk of enemy action disrupting the operation. Hartley thought it might be possible to use submarine cable technology to contrive a cable without a core that could be deployed by a cable ship. Fraser encouraged Hartley to develop this idea further and promised him his full support. So on the 16th of April 1942, Hartley called on the managing director of Siemens Brothers, Dr. Henry Robert Wright. Wright considered the concept viable and immediately arranged for his Woolwich factory to design and make a 200-yard test length, which could withstand an internal pressure of 500 psi. The test length was manufactured in the works power cable shop on an existing machine and from materials that were already in stock. It consisted of a 2-inch tube of hardened lead reinforced with 2 layers of 10mm steel tapes and over-armoured with galvanized steel wires. Production was completed within a week, and then a rigorous static testing regime commenced, including strain and pressure tests to failure. The results were promising and demonstrated that a much higher working pressure of up to 750 psi could be achieved. The design of the cable was based on Siemens Brothers' experience of developing gas-filled power cables, combined with their vast experience in making and laying submarine cables. The design concept was intended to deliver 30,000 gallons a day over the 20 nautical mile span from Dover to Calais. Just 15 days after the initial contact with Dr. Wright, a handling trial took place at Woolwich. It showed that the test sample could be coiled into a tank, loaded onto a cable ship, and discharged back into the factory without impairing its performance. These tests were witnessed by Geoffrey Lloyd and the service chiefs involved in the project. This included the coiling of the cable on board the post office cable ship HMTS Alert. That stands for His Majesty's Telegraph Ship, by the way, anchoring off the works in the River Thames. The visiting party included Lieutenant General Bernard Montgomery, seen here on the far left. Lloyd requested a short sample of the test cable that he could take to show the Prime Minister, Winston Churchill, and shortly after this visit, instructions came down from 10 Downing Street for the project to proceed with all speed. It was given the code name Operation Pluto. The Post Office, the Admiralty, Combined Operations, the War Office, and Anglo-Iranian were called together at Petroleum Division HQ to arrange the manufacture of further lengths and prepare a complete test program. Anglo-Iranian undertook on behalf of the Petroleum Division to supervise the implementation of the whole project. Siemens Brothers, without waiting for official orders, quickly produced more cable. As secrecy from the enemy was paramount, the cable was given a code name HASS, an acronym derived from Hartley, Anglo-Iranian, and Siemens. One of the most important features of this project was the necessity for the program to be carried out in absolute secrecy. As if the information were to have leaked concerning the nature of what was being planned, the enemy would have taken any risk to prevent the cable being completed or to destroy it when it was being laid in the English Channel. Elaborate precautions were put in place. The power cable production area at the Siemens works was isolated, and special passes were issued to everyone, whether senior management or factory worker, who was required to enter the area. The secure area had its own air raid shelters, shown in red. In addition, the staff engaged in the work were called into the factory library, where the works manager informed them that they were to be engaged in a job vital to the war effort. Everyone whom it became necessary to allow to enter the secure area was compelled to sign the Official Secret Act. and it appears that government security officers were brought in to test the strength of the systems in place. They made repeated but unsuccessful attempts to enter the restricted area of the works. The next section of test cable manufactured was 1,100 yards in length. On the 10th of May 1942, it was laid by HMTS Alert in a loop off Chatham in the River Medway. The ends were brought ashore to pumps borrowed from the Manchester Ship Canal Company, and pumping tests at 600 psi commenced. However, after 2 days, faults occurred in the cable. So the cable was recovered and the defective sections examined by the Post Office, Siemens Brothers, and W2 Henley & Co. Under normal circumstances, Henley's would have been a major competitor of Siemens Brothers, but it was at Siemens' suggestion that Henley's was invited to join the project to provide additional manufacturing capability, as its factory at Gravesend was also adjacent to the river, which facilitated transfer of cable to the cable ships. The collaboration between commercial competitors would continue throughout Operation Pluto. The cable failure mechanism was quickly identified as the extrusion of lead through gaps in the 2 layers of helical steel strengthening tapes, due to them being misaligned in certain places along the cable. To resolve the problem, the combined resources of Siemens and Henley's research and design development departments, together with the Post Office and the National Physical Laboratory, were mobilized. The result was a revised specification, and this was drawn up within 2 days of the failure mechanism being identified. The new design comprised a lead tin antimony pipe with 2-inch internal diameter, wrapped with 2 layers of paper tape, 1 of cotton, 4 layers of steel tape, right-hand lay, jute helically lapped steel wires, left-hand lay, and further layers of jute covered with whitewash. The opposite layers of the tapes and the armor wires were designed to make the cable torsionally neutral, so that it would not twist under handling or the influence of internal pressure. This design was calculated to allow for an internal pressure of 1250 psi. Lengths of the design were then ordered from both Siemens and Henley's. In June 1942, test lengths from both firms were laid by the Post Office cable ship HMTS Iris in a water of similar depth to the English Channel in the Clyde estuary. Siemens cable was the first to be deployed, and it was laid with the central core containing only air at atmospheric pressure. After the cable was recovered from a depth of 33 fathoms, it was pressurized to 90 psi, and it appeared that the cable was leaking, as after the cable had been filled with water, the applied test pressure would not remain steady. In addition, on later examination, water appeared on the outside of the cable, seeping through the outer jute serving at several places along its length. These locations were stripped down to the lead tube, where it was found to have been pressed in on itself into a kidney shape. The reason for this was that the tensile load applied to the cable, both on the forward drum engine and when passing over the bow sheave, had deformed the circular lead tube into an oval, and the external hydrostatic pressure had then further crushed the deformed tube. Because of this, some water became trapped in the space formed between the lead pipe and its steel tape protection. Under application of the test pressure, the lead pipe had begun to return to its circular form, and this pushed the trapped water through the outer armouring and serving, giving the impression of leaks. The problem of the collapsed core was overcome by laying the Hass cable filled with water, pressurized to 100 psi. This gave the Pluto team the confidence to make the decision to manufacture 6 operational lengths of 26 nautical miles, plus an additional length for a full-scale trial in the Bristol Channel, where conditions of tide and depth of water can be found that were more severe than those that would be encountered in the English Channel. Full-scale production of the 2-inch cable commenced at the Woolwich Works on the 14th of August 1942. And the first completed 30 nautical mile length for the Bristol Channel trial was ready for loading by the 30th of October. It had an overall diameter of 3 inches and weighed approximately 1,050 tons. There was no existing cable ship that could handle and deploy this extremely heavy cable, and any vessel large enough to carry it would have too great a draft to get close enough inshore to land the cable ends. Therefore, the Admiralty and the Ministry of War Transport Division made available the SS London, a coaster of 1,500 tons. She was fitted out to lay the Hass cable and renamed HMS Holdfast. Equipped with Johnson & Phillips cable gear lent by the post office, she was fitted with large cable tanks plus specialist bow and stern sheaves. Siemens suggested to the authorities that Commander Henry Treby Healy should be made available for the laying operation and perhaps given command. He had until recently been in command of the company's cable ship Faraday II, but she had been destroyed by enemy action off Milford Haven on the 26th of March 1941. Treby Healy survived the attack and had been seconded to the Royal Naval Reserve. He was an ideal choice as he had great experience in laying of heavy submarine cables, and so Siemens' suggestion was readily accepted. This just left the problem of landing the shore ends. It was concluded that these needed to be landed by smaller vessels, and a quick coupling or joint would be required to join the main cable to the shore end cable. 2 satisfactory types of armour joint were developed. The first consisted of a conventional submarine cable laid in splice. This splicing method was used for factory assembly and shoreside repair work. Altogether, some 40 splices were made by Siemens jointers, but the job proved to be too time-consuming and demanding too great a skill to be practicable when laying under fire. Therefore, a mechanical coupling was essential. The design of such a coupling was a complex issue, and several initial designs were prepared. However, after due consideration, the Siemens design was adopted, and the company became the sole supplier of all couplings used in connection with Operation Pluto. Each coupling had a complete pressure termination for a single cable end and could be fitted in about 2 hours by a skilled technician. 2 couplings could then be brought together for a straight-through connection, and assembly could be completed in about 30 minutes. Couplings were fitted to each cable end on the ship, on shore ends, and on spare sections for repair. The couplings design included bursting discs of thin copper, which were incorporated in the joint to hold the water pressure that was used when laying the cable. Once the full length was assembled, these discs could then be burst by increasing the internal water pressure, allowing flow through the complete pipeline. Throughout the autumn of 1942, tests were conducted at the experimental establishment at Westward Ho in an attempt to find ways of handling the shore ends with craft that could be operated close to the beach. The most promising method devised was to mount cable drums on horizontal axles in landing craft designed for landing armoured vehicles, with a view to paying the cable out over the lower bow ramp with the craft going astern. This method was used as part of the full-scale Bristol Channel trial. With all the necessary building blocks in place, the full-scale rehearsal of Operation Pluto took place on the 29th of December, 1942. A 30 nautical mile length of Hass cable was successfully laid across the Bristol Channel at 5 knots by HMS Holdfast. However, greater difficulty was experienced in laying the shore end cables at Ilfracombe and Swansea. This was due to the lack of manoeuvrability of the landing craft when going astern with a heavy cable over the bow. Further development work would be required before the trial cable could be completed. As a result of a conference convened in January 1943 to evaluate the rehearsal, it was agreed to adopt an alternative method of landing the shore ends. This would employ the industry standard technique of coiling sufficient cable in the hold of a barge, specially fitted for playing out over the stern through hand-controlled compressor gear. A number of Thames barges and their crews were seconded for this task, and the shore ends for the trial system were completed by the end of March 1941. Meanwhile, a pumping station had been erected on the sea wall at Queen's Dock in Swansea and connected to the National Oil Refinery's tanks. A receiving terminal with tanks, pumps and loading racks had also been built in Watermouth Bay near Ilfracombe. After satisfactorily testing with water, the first petrol ever to be pumped through such a long sea line reached Watermouth on the 4th of April 1943. Geoffrey Lloyd was there to witness it arrive, and a few days later he took a sample to the Prime Minister. It had been planned that the vulnerability of the cable to bombing or depth charges and the possibility of needing repairs should it be dragged by a ship's anchor would be evaluated. However, a German air raid on Swansea proved that the cable was not damaged by a bomb that exploded within 100 feet of it. Also, during a gale, a ship in the Mumbles anchorage dragged the cable with her anchor. HMS Holdfast was deployed and had no difficulty in locating the cable, cutting out the damaged portion and completing the repair with a new length of Hass cable. In order to prove the reliability of the cable and the pumps and to train the staff, pumping continued day and night. Initially, the system was operated at the design pressure of 750 psi, but later was increased to 1500 psi. At that pressure, 56,000 gallons were pumped from Swansea to Watermouth each day and distributed by the Petroleum Board around Devon and Cornwall. Early in the Hass cable development programme, an alternative approach was introduced and worked on in parallel. Bernard J. Ellis, Chief Engineer of the Burma Oil Company, was engaged in Hass cable programme, and when he saw that the cable was extremely stiff in short lengths but flexible and easily manageable in long lengths, he suggested that a steel pipe could be used for Pluto, as he had seen samples of small diameter pipes that were flexible when handled in long lengths in the oil fields. He would later team up with Harry A. Hammack, Chief Engineer of the Iraqi Petroleum Company, to develop this project. A prototype of Ellis's pipe design was fabricated at J&E Hall in Dartford. The mild steel pipe had a wall thickness of 0.212 inches and an internal diameter of 3.5 inches. It was produced in 30-foot lengths, and these were welded together. This prototype quickly proved that the pipe had sufficient wall thickness to handle the necessary pump pressure. It could be bent around a wheel of 30 feet diameter and pulled off again, remaining relatively straight without kinking. And sections could be flash welded together to provide any length required. However, with this bending diameter, it could not be handled like cable and stored in a cable ship's tank. Ellis therefore suggested on trunnions on the deck of a hopper barge with its low portion protruding into the sea through the hopper doors could be utilised to deploy the pipe. An alternative approach also adopted was a huge floating drum like a gigantic cotton reel, capable of carrying any quantity of pipe likely to be required. Model tests of this floating drum concept were carried out at the National Physical Laboratory tank at Froude. These tests confirmed that such a vessel could be towed at sufficient speed without yawing, and in a witty wordplay, the floating drum became known as the Conan drum, shortened to Conan. Preliminary work confirmed that the pipe could be laid up on the drum and pulled off without kinking. The sections could be welded together with absolute reliability, so long lengths could be carried and laid by either the wheel and barge or the Conan system. As the Hass cable was as yet unproven, and there was significant concern as to whether there would be sufficient supplies of lead available to complete the Hass program, having a complementary method was considered desirable. So it was decided to proceed with this approach in parallel. This pipe was given the code name Hamel after Hammock and Ellis, although after the war, Ellis successfully asserted his claim that he was the sole inventor. 2 factories were set up at Tilbury to manufacture, store, and then wind the Hamel pipe onto drums. A hopper barge, later called HMS Persephone, was converted to carry the drum, and a column drum was also constructed. Stewart and Lloyd took control of the 2 Tilbury factories and oversaw the design and construction of the pipe. At the same time, the Director of Naval Construction took responsibility for fitting out HMS Persephone, the design of the column, and the supervision of its construction. The 2 adjacent factories in Tilbury manufactured 40-foot lengths of 3.5-inch diameter mild steel pipe, and then welded them into 4,000-foot lengths. During welding, these pipes were pushed down conveyor channels, then thrown off onto the storage racks. The success achieved by the Bristol Channel trial had already led to the consideration of increasing the diameter of the core of the Hass cable to 3 inches. This dimensional change had been suggested as it would offer a significant increase in the capacity that would reduce the number of cables needed to reach the required supply target. The requirement for a 3-inch cable to provide the shore ends for the Hamel pipes added to the reasons for progressing this design modification. The design of the new cable was similar in most respects to the 2-inch cable, with the exception of the increase in tube diameter, and the steel tapes were increased to 22mm in thickness to deal with the greater hoop stresses that the cable would need to withstand. The final overall diameter of this cable after armouring was about 4.5 inches. Work on the 3-inch design commenced at the Woolwich Works in September 1943, and in parallel the coupling design was adapted. New designs were developed for the 3-inch cable, and a modified version to fit the ends of the Hamel 3.5-inch Hamel pipe was also developed. By the end of 1943, full-scale production of both the Hass cable and the Hamel pipe had been authorised, and responsibility for the operational stage of Pluto was passed to the Petroleum Warfare Department under Major General Sir Donald Banks, and Force Pluto, set up by the Admiralty under the command of Captain John Fenwick Hutchins, Royal Navy. On the 29th of April, the decision was taken that no further lengths of 2-inch Hass cable should be made, and that the 3-inch design, then undergoing works test, should be thoroughly trialled in order to maximise the opportunity of obtaining the advantage that it could provide, almost trebling the throughput of the 2-inch cable. In July 1943, the Chiefs of Staff Committee confirmed that Operation Pluto was to be made a high priority. Up to this point, the plan had only involved a pipeline from Dungeness to Boulogne, but now a second line from the Isle of Wight to Cherbourg was added. Plans were put in place for pumping stations to be built at Dungeness and Sandown on the Isle of Wight. Unknown to the members of Operation Pluto teams, this was an indication that the D-Day landings were being planned for Normandy. The decision to lay a pipe from the Isle of Wight to Cherbourg required much larger quantities of cable and pipe, and so arrangements were made to increase British manufacture as much as possible, but also to obtain 140 nautical miles of cable from the USA. In addition, it was planned to duplicate the Tilbury factories for welding, storage and winding Hamel pipe in the USA. However, when the progress made in the UK with the Hass cable and the Hamel pipe was seen by Ike, General Dwight David Eisenhower, Supreme Commander of the Allied Expeditionary Force in Europe, he decided to amend the American scheme and concentrate on helping the British programme by supplying cable to the UK's design and providing additional pumping and auxiliary plant from the USA. The Isle of Wight to Cherbourg route involved a sea crossing of about 70 nautical miles, instead of the 26 nautical miles originally visualised. This made necessary the provision of larger cable ships and the use of a connon, which would be loaded until the axles were awash. Following a successful trial lay of the 3-inch HASS cable, Operation Pluto obtained 3 more ships to convert and fit cable gear. HMS Algerian, HMS Latimer, and HMS Sancroft were required to carry up to 100 nautical miles of 3-inch cable, weighing about 6,400 tonnes. 6 Thames barges were also converted and equipped to handle the shore ends. In addition, smaller auxiliary vessels were added to the Operation Pluto fleet. Tests using a model connon showed that it could be handled when loaded with 70 nautical miles of Hamel pipe, provided that 2 of the largest ocean-going rescue tugs, the Bustler, were used ahead and a smaller tug astern for steering. The production of 5 more connons was then put in hand. When fully loaded with 70 nautical miles of Hamel pipe, each connon weighed 1,600 tonnes, or the equivalent of a Royal Naval destroyer. The development and manufacture of the HASS cable and the Hamel pipe, together with the conversion of the vessels and the construction of the connons, was completed in just over 2 years. This would have been an exceptional achievement in peacetime, but it was carried out in what appears to have been complete secrecy. Given the number of organisations that had to collaborate, it is impressive that the Germans did not get wind of Operation Pluto or its objectives. However, there was a war going on, and throughout the development programme and right up to the end of the war, London was the target of bombing raids. All the major Operation Pluto manufacturing sites were on the River Thames at Gravesend, Tilbury and Woolwich, close to major docks and thus obvious targets. The Luftwaffe's general approach to bombing raids on London was to gather their planes in the North Sea off the Thames estuary or in the Channel off of Folkestone, then follow the river or the A20 into London. In both cases, the Siemens Brothers works at Woolwich was directly in the line of fire. Although Siemens Brothers were predominantly a British company at the start of the war, the German counterpart still held a large equity stake, and there were still a few German-born employees. The 2 companies had continued to collaborate on development programs right up to the outbreak of war. And thus the Nazis knew all about Siemens Brothers and its products. So the Woolwich Works became a specific target. This can be confirmed because of a unique photo discovered by Allied troops when they liberated the Luftwaffe headquarters in Belgium. Though not that easy to see, there is a thick red line on this photo that outlines the works at Woolwich with great accuracy. The index at the bottom gives descriptions of the various types of buildings and in some cases information of what they were used for. None of these footnotes refer to Operation Pluto or the HASS cable. There is no doubt that the Nazis considered the Siemens Brothers works an important target, and while all 3 sites had to deal with German air raids, the Siemens works probably suffered more than the others. The first air raid on London took place on Saturday the 7th of September 1940, commencing at 1700 that evening. This was the start of what was known as the Blitz, and a bombing campaign that continued with decreasing intensity until the end of the war. In October 1945, from detailed ARP records, a plan of the works was marked up with the number of high explosive missiles of various types that landed on the site and their locations. In addition, the incendiary bombs that were dropped on the premises were scattered in such large numbers that it was impossible, after the first 1,000, to keep accurate records of their location, but their general distribution was indicated on the plan. Although a great number of landmines were dropped in the Woolwich area only one landed on houses in Harden's Manaway, 50 yards to the west of the works, shown in the plan with a parachute attached. So I guess very few of us can actually visualize what this all meant and what these attacks were like. So let's have a look at some of the destruction that they caused. During the war, the Woolwich site was hit on no less than 22 occasions. And the research department of Blackheath was also damaged by high explosive and incendiary bombs. After the 7th of September 1940, the bombing of London continued with great intensity for a continuous period of 90 days. Records show that these intense air raids by bombers lasted for a period of 6 months, but occasionally heavy raids persisted throughout 1941. Once the Battle of Britain was won, the daylight raids ended, and although night raids followed into 1942, they grew gradually weaker and proved less accurate, so very few high explosive bombs were dropped within the works, although the damage caused remained high. Thousands of incendiary bombs fell on the works and inflicted significant damage. The night raids continued spasmodically until the start of the V1 flying bomb attacks. The V1 flying bomb attacks commenced on the 13th of June, 1944. They continued day and night until they were replaced by the V2 rocket. The first V2 hit London on Friday, the 8th of September, 1944. And the attacks continued until the launch sites in mainland Europe were finally overrun by Allied troops at the end of March, 1945. There were, of course, many bombs, flying bombs and rockets that landed in close proximity to the boundaries of the Siemens works. And although these caused only limited blast damage to the works, they did cause serious stoppages to production by interfering with utilities such as gas, water, electricity, and telephone. Apart from the incidents that occurred in and around the factory, production was also adversely affected when there were attacks on the district as a whole, or when enemy planes were over the works, as many thousands of man-hours were lost through the employees having to take cover in the works' air raid shelters. A further disruptor was injuries to employees and damage to their houses in the local area. Remarkably, the Siemens works got through the war with only 3 fatalities and 1 serious injury requiring a leg amputation. Despite all this enemy action, the HASS cable development and manufacture was successfully completed in time to meet the required milestones of Operation Pluto. As is well known, the D-Day landings, codenamed Operation Neptune, took place on 3 beaches, Gold, Juno and Sword in Normandy on the 6th of June, 1944. The original plan was to capture Cherbourg by D-Day +8, but due to stout German resistance, this was not achieved until the 27th of June. Because of the extensive damage in capturing Cherbourg and the need to clear the harbours of mines, the start of Operation Pluto was further delayed. The code name for the route from the Isle of Wight was Bambi, and the first 3-inch HASS cable was laid from Shanklin Chine on the Isle of Wight to the tip of the Cherbourg Peninsula. Despite some initial difficulties, it was successfully installed by the 22nd of September and was quickly followed by a Hamel pipeline on the 29th of September. These were followed by another HASS cable and Hamel pipeline. Each was 70 nautical miles in length, and petrol was pumped through these pipelines to support the Allied advance along the Channel coast to Boulogne and Calais. The advance of the Allied armies into Belgium and Holland was so fast that it became essential to shorten the lines of supply, and so further pipelines were run across the Channel on the original planned route from Dungeness to Boulogne. This route was codenamed Dumbo, and the lines from Dungeness will run to a beach inside the outer harbour of Boulogne. This saved vital time by obviating the need to clear the heavily mined beach at Woolwich that had previously been chosen as the landing point. The change of landing involved a longer run of 23 nautical miles with a more difficult approach, but techniques were quickly modified, and once these had been perfected, lines were laid and commissioned without incident. The first HASS cable on this route was laid by HMS Sandcroft on the 26th of October, and pumping began the same day. By December 1944, 4 3-inch and 2 2-inch HASS cables had been laid on this route, plus 9 3.5-inch and 2 2-inch Hamel pipes with HASS cable shore ends had also been laid. Once the Boulogne receiving station had been established, Bambi was shut down. Each of the 3-inch lines from Dungeness were capable of delivering about 400 tons a day, or 120,000 gallons. They were supplied and installed sufficiently quickly to keep ahead of the capacity required to be pumped from Boulogne into the French interior. The total length of the pipelines laid on the Boulogne route was 500 nautical miles, which provided a total capacity of more than 4,500 tons, or 1,350,000 gallons per day, and 1 million gallons a day were pumped across the channel for some weeks. As the Allied armies advanced, the lines were extended inland through 6-inch vitricular pipes. Eventually, petrol could be pumped from Boulogne to Calais, Ghent, Antwerp and Eindhoven, then across the Rhine to Emich. From Cherbourg, the route was extended to Chartres, then south to Paris, into Luxembourg, crossing the Rhine at Mainz and partway to Frankfurt. The pipeline's terrestrial extensions were constructed under the control of Quartermaster General of the Allied Forces, General Sir Thomas Sheridan Ridley Webster. The final joint was completed on the 10th of April, 1945. Production of the 3-inch HASS cable continued at the Woolwich Works until September 1944. By then, Siemens had completed the manufacture of a large number of operational lengths of 2-inch and 3-inch HASS cables. One of the longest sections of 3-inch cable was 35 nautical miles and weighed over 2,200 tons when the core was filled with water. The factory coil for this was 10 foot high and 65 feet in diameter. In 1943, due to earlier bomb damage and the space required for coiling such long lengths, a new building with extra strong cable sheaves and hauling equipment located in the roof was erected. Also, a long counterpoised steel arm was designed and fitted to facilitate the handling of this extremely heavy cable. The cable was loaded onto ships moored in the river and hauled on board across the catenary by the ship's cable engine. Altogether, Siemens manufactured and delivered over 200 nautical miles of 2- and 3-inch HASS cable for the Petroleum Warfare Department. Some 280 couplings were supplied, and with each set of 2 couplings, a set of specialist tools was provided together with numbered spare parts to facilitate the rapid trimming of cable ends and fitting of couplings. At the beginning of this talk, I said that Operation Pluto was pivotal and a key pillar of the liberation of Northern Europe by the Allied armies in 1945. There were 3 key pillars that underpinned the Allied victory, and Operation Pluto was the third of these. Without adequate fuel supplies, no matter how successful the military campaign, the Allied forces would have quickly reached the limits of their logistical supply chain and would have been forced to dig in. Had Operation Pluto not happened, the advances inland after D-Day would have bogged down in a new Western Front closer to the beachheads, and this would have brought the Germans vital time to prolong the war. German military strategists understood that the enormous, highly mechanized Allied armies would have a voracious appetite for fuel. They assumed that this demand could not be met unless major channel ports were captured in which bulk tankers could be docked to supply the forces. This is why the German garrison at channel ports, such as Cherbourg, were instructed to hold on until the bitter end, and why towards the end of the war, Antwerp became the focus of V1 and V2 rocket attacks. Without timely intelligence of the project, which was never forthcoming, the German High Command could not have anticipated the massive quantities of piped fuel that Pluto delivered. Therefore, alongside its incredible engineering achievements, the measures taken to keep Operation Pluto secret were vital to its success. The contribution made by the employees of Siemens Brothers to Operation Pluto in such difficult and dangerous circumstances was a major contributory factor to its success, and their courage and skills should never be forgotten. The Siemens Brothers factory was shut down in 1968, making over 8,000 employees redundant. In the late 1970s, the secure area of the works where the Haas cable was manufactured was demolished to make way for the construction of the Thames Barrier. And from 1982, the Barrier Control Building has stood in the centre of this area. Since 1968, some of the site has been redeveloped, but the vast majority has lain idle. However, the owners of part of the site, Royal London, are working with property developer U&I plc to regenerate the 5 acres to the northwest of the remaining site, between Faraday Way and Bowater Road, in a project called the Faraday Works. This area is adjacent to the area where the Haas cable was manufactured, and I for one hope they can find a way to commemorate this important historical event in the redesign of this area. Regrettably, when the works was closed down, the vast majority of the company's records dating back to the founding of the site and including the company's extensive library were thrown into skips. However, thanks to the work of the late Walter John Ford and Brian Middlemass, over a period of 10 years, what remains of the Siemens history has been brought together and donated to the Royal Greenwich Heritage Trust as the Siemens Brothers Engineering Society archive. This invaluable record can be consulted by appointment at its archive in Unit 15 at Anchorage Point. There you go.
Thank you, Stuart. That was fantastic. Thank you very much.
Unshare?
Yes, unshare, and we can come back to video. Thank you, Stuart. Thank you. That was brilliant. I mean, we have a question. If you want to ask questions, if you move your mouse across the screen, there's a thing saying chat, and that will open up a box and you can type in questions. And Tony Cooling has already asked a question that I was going to ask if he hadn't. Is there anything left of the pipes? Any physical evidence of them, either across the channel or in Woolwich?
Nothing in Woolwich. There are some on, you can see on, if you go on Google and search for them, there are still some on the Isle of Wight that of the terrestrial pipes. They've all been painted blue and look very pretty and have Pluto on them. So they're not originals. No, all the pipelines in the sea were recovered afterwards, or the majority of them. So
reclaiming the leads and the steel and the...
I'm not sure about that. I think they were picked up for strategic reasons. Probably there was connections, as you know, connections between France and England were a major issue at that time. Mr. de Gaulle wanted isolation from us, so that may have been part of it.
De Gaulle didn't come in until 58, so there was a long time between the end of the war and de Gaulle coming in. But yeah,
they all were picked up. Whether that was, I mean, obviously after the war there was a need for materials because we were in quite a parlous state, so that might have been part of it. But if you go back through the records, there's very little information about why and how they were recovered and where the materials went after they were picked up.
John Usher says Tim Whittle's book fueling the wars challenges the conventional view that Bambi at least delivered nothing to Normandy. Any view on that, Stuart?
I think this is one of the things, because of the delays to get Bambi running. There was a suggestion that it didn't do very much, but it did help with supplies to provide the army from the beachheads to go along the coast. Obviously, Dumbo was the biggest part of it, but it was never really got going without the Sentinel connection.
Dumbo was the one that went across the Straits of Dover, right?
Yeah, Dumbo is Dungeness to Boulogne.
Was that what I was thinking when you were talking about the initial idea of Dungeness to Boulogne? Was that part of the misinformation strategy, that they wanted to give the view that the invasion was going to be on that sort of part of the coast around Calais, Boulogne, so that the Nazi forces would be focused there, and that carried on right through till the 6th of June 44. Was that part of the strategy, that they wanted to show that that's where they were going? Because they had all these sort of cardboard tanks and stuff like that all around the Kent fields.
Yeah, I didn't go into the camouflage, and there's obviously not a lot available as to what the thinking was.
Yeah.
But obviously the Germans would have thought that the crossing would have been at the shortest point, and they weren't going to dissuade them from that. How much what went on at Dungeness for that was part of disinformation, and how much in the end it was absolutely vital to shorten the length and provide the fuel that they did. There is no doubt that Dumbo on its own provided so much fuel for the army that it shortened the war. I think you can debate whether Bambi was very successful, but I think if you look at it, the amount of fuel that was actually fed into the beachheads allowed the advance along the coast to Boulogne and Calais. But of course, I'm not a war historian. I'm a submarine cable man.
Exactly, which takes me on to what my next question was going to be. Is there a technological link between Pluto, the technology developed within 3 years for that, and the sort of modern pipes that are used for electricity and gas? A lot of the same sort of companies that develop subsea cables for telecoms also do cables for other things. Is there any sort of connection? Is there a sort of heritage?
I'm not sure that there's anything in terms of flexible pipes for the oil and gas industry.
Right.
Obviously, some of the lessons that were learned can be carried over. But as I said in the presentation, the skills that allowed them to develop this cable came from working on gas-field power cables.
Right.
And also nearly 100 years of submarine cable technology.
Right. Yes, indeed. Debbie O'Boyle says, is there a link between the names Persephone and Pluto? Well, I mean, the Pluto are all Disney names. So
Greek mythology link, yes.
Yeah, well, quite, yeah. And why did they choose to name everything after Disney? But there we are. That was the 40s for you.
I don't think records exist that explain the choice of names. I mean, I was actually working with Bill on a couple of presentations for this, and it struck him after several months, which I'd seen immediately, that the Conan drum was a play on words. And Bill suddenly kept, when we were editing, I think about the third version of my Subtel Forum article, or our Subtel Forum, he suddenly said, I've just spotted what Conan drum is.
What is it? Explain.
Conundrum.
Conundrum! Oh, goodness, right, okay. Oh, God, I'm being so dumb tonight, Stuart, thank you.
Well, I saw that immediately, but as I say, it took Bill nearly a month of working on drafts and things.
Bill's here.
And I said I thought it was obvious, but he said no, it isn't.
Right. Tony Cooling again says, what type of pumping was used? Was there a big explosion risk at those pressures?
Obviously, the pipes and the cables themselves were pressure tested, and so were all the joints. So all the safety measures for doing that were, remember, there was a big oil and gas industry anyway. So the technology for pressure testing welds and things like that for welded pipes, and also the couplers, obviously it was always a risk. And of course, there was a risk of anything getting damaged. I mean, I didn't go into the camouflaging of the pump stations and all that sort of thing, but they had camouflage officers seconded to Operation Pluto. And the pump houses on the Isle of Wight were in ice cream factories and in a bungalow, a normal house. And
right.
It was an incredible piece of subterfuge.
Right. There's an island-wide shortage of ice cream, but they weren't making ice cream anyway. Oh, I suppose. Okay. Isabel says, was it entirely surface laid? And do they consider any burial of the cable for increased protection? I mean, surface, I presume she means on the bed of the sea.
No, absolutely not. The whole point was to lay the pipe quickly so the ship didn't get bombed. So 5 knots was about the payout speed, so you wanted to get across in 4 hours.
Wow, yes. And then you talked about landing, extending it into France and Belgium and to Luxembourg after the invasion. Yep. I mean, was that picture you showed was just along the side of the road? Was that?
Yeah, just laid alongside the road and coupled up. Yeah, it was incredible.
So, I mean, that could have been sabotaged if there'd been any.
Well, if the Germans could have got behind our lines, they were in retreat then, I suppose.
Or people just wanting fuel for their own private use, but there we are. Yeah.
Surely the French aren't like that. French don't do sabotage, surely not. I know they throw cobblestones around.
Yeah. Okay. Type in any more answers if you've got. We've probably got another 5 or 10 minutes. One of the things I was wanting, you mentioned secrecy and security. And I couldn't help remembering this book here, which is, I've mentioned before, it's Anthony Sampson's book about ITT, which was owned STC, which later bought the factory in Greenwich in the 70s, I guess. And Anthony Sampson talks about the wartime history of ITT. I mean, it was a scurrilous company. Apologies to anybody who worked for it, but they were illegally working via Switzerland to control their factories in Germany from the United States, as well as their factories in the UK, which included, I guess, a lot of telecoms factories around London and elsewhere. I mean, of course.
College.
Yeah, how did they manage to ensure? Was there any connection between Siemens Brothers in Woolwich and via neutral countries, parent company in Berlin?
I can't comment. None of the documentation that I've researched has anything to say on that subject. I mean, all the stuff that I've used to put this together is now available in Royal Greenwich Heritage Trust, because during lockdown, a number of people have contacted Bill and myself, clearing out their attics and saying, I found this stuff, do you think it's any use? And mainly they've sent it to me because I'm in this country, and we go through it, and some of it's useless. And the Siemens report on the bomb damage is an absolutely superb document with 48 images in there. And
which is where you got your photographs on this book.
Yeah, and all the detailed records of the people involved, so the whole teams of the ARP and fire crews in the factory. So for people whose grandparents worked there, that can now be seen. The trouble with Royal Greenwich Heritage Trust is there's nothing online, so unless they know what you're looking for, it's very, very difficult to get hold of it.
Yeah, it's a bit Victorian, isn't it?
I have a complete catalogue of what's in the Siemens, thanks to Mary, actually. She lent it to me and I haven't given it back. It was the Siemens Engineering Society, Siemens Brothers Engineering Society archive. I have the full documentation of what they put together and donated.
Yeah. You mentioned all the records going into a skip in Woolwich
Yeah.
when it closed down. I was going to say I couldn't believe it, but then it was owned by GC at the time, and they were just ruthless.
Yeah, Weinstock just wanted it cleared.
Yeah.
I spent a lot of time with Brian Middlemass before his unfortunate death, and he was very upset about that. That couldn't be saved. A tremendous loss of history.
Yeah. Anthony's iPad, presumably Anthony, has a great idea. Dumbo is nearly done from Dungeness and Bo from Boulogne. Is that a coincidence?
Well, the other one was called Bambi. I think it probably is.
Right.
Bambi was the first one, but yeah.
Maybe somebody had a bright idea sitting there looking at a map. And also says, how were the armies in North Africa supplied? Well, presumably from Iraq and Iran.
Oh yeah.
Yeah.
Well, plus the fact that we still had ports available in Tripoli and Benghazi then to bring fuel in by tanker.
Yeah, but there was an overland route via the Middle East, I would guess. Via Iraq and Iran, both of which were under British control at the time, straight into Egypt and the rest of North Africa. Yeah, right, any more questions? Yeah. Tony says, and I echo him, fascinating presentation. Many thanks indeed. Thank you, Tony. Any more questions before we close? Because it's now 8:45, so it's been a great hour and a quarter. And I will, at some point, probably the week after next, when I've got a week off, I will sit and edit some of this video and put it up on our YouTube channel. And there's Stuart's presentation on the origins of the Siemens factory and the whole heritage that you delivered last December, I think it was. That's up there already, but there's lots of other stuff from me, from Mary and other people. There'll be more stuff up there shortly. Anything else? Any other questions? Debbie says, thank you very much. Thank you, Debbie. Before we all adjourn to the pub. No, we can't adjourn to the pub. Sorry, we can't, can we? No, I will say thank you very much. The next talk from the Greenwich Industrial History Society is me, which is on the 14th of December, which is also a Tuesday. And despite the fact that Mary says it's the canals of Southeast London, or South London, I keep saying it's the failed canals of South London, because they're all
failed. Find what is
failed. And I'm going to compare North London and the Regent's Canal and Paddington Basin and all that sort of stuff with the sort of abysmal remains we have of canals here. But there are lots around. And
got a little bit of the one in Woolwich, just a little bit, and they've taken the water out of it. I think Debbie knows more than I do.
There are some bits around Sydenham and Forest Hill and Penge as well, which I'm going to go and photograph again over the next, or week after next. But there is also a lot of telltale remarks if you know what you're looking for. There are bridges, there are remains, the sites of locks all over South London. And I noticed something in one of the local Facebook groups a few weeks ago, a picture from the canal going through Forest Hill, just by Forest Hill Station, and the person said, who knew there was a canal in Forest Hill? Well, yes, there was. And so that will be on the 14th of December, 4 weeks' time or thereabouts. So thank you, Stuart. Thank you very much indeed. Superb talk, says Valerie Ellis, and I echo that. And thank you very much indeed. Look forward to continuing to see you all at Greenwich Industrial History Society meetings. Probably still going to be on Zoom, as Mary was saying earlier. Do you want to say a bit more, Mary? Because I think that was before a lot of people joined, that it's actually, we've got such an international gathering here, and we get
that's right.
all around the world. Go on, Mary.
Absolutely.
Yeah.
I mean, I'm hoping we can do something else about Enderby's in towards the next year. I'll talk to you about it, Alan, but you know, we could do something quite prestigious and you know, it's a day event, I think.
I think that's a great idea. There's so much around this area.
Yeah.
And we could either do it, there are lots of good venues in the area that we could use, and I think we should make the most of it. There was going to be a talk in May 2020 about my first version of my talk about the subsea cables of Greenwich, Enderby and all that sort of thing. And that got cancelled because of the pandemic before we all discovered Zoom. So if we can all meet together in 2022, let's do it. Join our Facebook group if you're not already, Greenwich Industrial History on Facebook, or look at our blog and you'll find everything we've got to offer for South East London and beyond. So thank you. Thank you, Stewart, and thank you, Mary.
Okay, we'll see you all next month.
Let's hope it'll show some interest in what you and I are doing there, and this valuable piece of history isn't lost when they redevelop the site.
Somebody says, do I know anything about the Royal Clarence Canal? And I have no idea where that is. I will look it up for my talk for next month. Okay, thank you, everybody. It's now nearly 10 to 9. Somebody going to say
Bye,
something?
everybody. See you next month.
Thank you.
I was going to say thank you, Stuart. It was a brilliant talk. Absolutely fascinating.
Thank you very much indeed.
And amazingly researched. It was really in a big context. Thank you. It was great.
Thank you.
You can find all the stuff now in the archives at the Royal Greenwich Heritage Trust now, because I can't lay any claim to inventing all of this. I was provided with the documents and it gave me something really interesting to do during lockdown. So now it's going to go on for a while with people emptying their lofts to get rid of stuff. I seem to be one of the targets for is this valuable? I think that's what they want to know in the first place. But we've been able to capture some really interesting stuff that I've never known about my own industry, which I've been researching for over 20 years. So the lockdown has had some upside as far as I'm concerned in terms of historical research.
We haven't been commuting, we've been doing useful research. Exactly. Thank you very much indeed, Stewart. Thank you. Stewart Ash.
Thanks very much. Thank you.
Thank you.
Bye. Thank you.
Bye.
Thank you, and good night to everybody. Good night.
Good night.
All right.